Hey, I'm Jan Kotek, author of MapDB. I want to apologize for the audio quality. I haven't figured out how to use external Bluetooth microphone yet, and it's a long time since I uploaded to this channel last time. I want to start uploading again, maybe mostly for the quick notes that do not really fit on the Twitter or blog, are too small for the blog post. Maybe some screencast in the future of coding sessions and so on. But today I would like to talk about MapDB 4 and what is happening there, and how the rewrite is going and why there is actually a rewrite. So if you ever used in MapDB, you know that it requires compaction. If it keeps running for several days or maybe months with loads of write, it becomes internally fragmented, and it requires complete rewrite of the storage. It's not really practical for many reasons, and kind of requires a new storage engine and some changes in the architecture to keep it stable over basically indefinite period of time. MapDB 1 and older versions of MapDB were really focused about saving storage space. It's a kind of legacy thing when the computers have like 100 megabytes and so on, but basically it was designed to consume to have as little space overhead as possible. The new storage engine in MapDB 4 is not as conservative, or it's a bit more wasteful. It's using fixed size pages with size of 256 bytes. If the record is smaller, it will be expanded. But because the pages are fixed size, it greatly reduces this complexity and allows sort of optimizations that wouldn't be possible with variable record length. I will link to get some background. There is really good talk about LMDB storage. That's a sort of inspiration for this new storage engine. I will link it in the description, so have a look. But MapDB 4 is simplifying this even more. Basically, the new version is focused on the continuous running. So the space allocator is simplified a lot. It shouldn't require compaction at all. But on the other side, the storage right now is fixed size. It means that at the startup and the time you create a database, you give it like 1 gigabyte of storage or 1 terabyte, whatever, and you cannot change that size of the storage while the database is running. It's possible to shrink it or expand it offline when the database is shut down, but it's fixed size. This sort of simplifies the internal design a lot, and I think it's much better for the continuous use on the servers and even some desktop clients where the space is not such a big issue. As I say, the major concern about this is reliability and avoidance of compaction. Another nice thing is that new storage engine, because it's using fixed size, it's so simple. It can bring more features. So it was designed with snapshots and time traveling and so on for on mind. So it will be possible to do proper transactions and rollbacks and maybe sort of do branching similar way as on Git, but with the data model. So as I say, this is possible because the old design was really simplified. The storage engine is much simpler, and it's much easier to reason and prove that it's actually correct, that it's not overwriting data that should be overwritten and so on. Another issue in MapDB 4, in older versions of MapDB, was write amplification. If you know MapDB, the way MapDB works is you take record from the storage, you deserialize it, you make some modification to it by making copy on heap, and then you serialize it back to the storage. That's a kind of problem with, for example, if you have a B3 node, B3 directory node that has array of items, and you update a single item in the middle, and you have to basically make loads of copies of the thing, and you update it multiple times. You have to make loads of copies and serialize them, deserialize them to kind of move them around and so on. Basically, MapDB 4, older versions of MapDB had a big problem with write amplification, and the things to solve it were just workarounds like write cache and so on. The new design basically allows, first it doesn't use serialization and deserialization at all. It's optional. You can still use the deserialization, but internally it's not using object input stream sort of thing like Java serialization, but it's using byte buffers directly. So you can go to the byte buffer and directly modify, let's say, third or fourth item in the array, and directly write it in the memory map storage. So basically this completely solves the write amplification in certain ways, and again it simplifies the design a lot because we don't need background threads and so on, background write workers and so on. Yeah, so direct inserts. Another thing in MapDB 4 is that I removed loads of stuff that wasn't necessary or wasn't really working. Maybe you know how I was trying to do concurrency by using segmented locking, basically sharding storage into several segments, and each of those segments would have its own log, and there was structural log and write log and so on. This was maybe working for like up to 2, 4, maybe 6 CPU cores, which was more than sufficient at the 2010 when the MapDB 1 was conceived, but it doesn't really scale up to like 64 cores, and it has loads of overhead with memory barriers, and basically it doesn't scale at all. I think it was actually slowing it down a little bit. So the current version is throwing away concurrency completely. It's using read-write log, so basically it allows multiple readers and single writer that will block everything, that will block all the reads. Similar SQLite is working similar way, but it's very simple to implement, very simple to prove that it's correct, and most importantly very simple to write unit test that will hammer, or stress test that will hammer it for the concurrency update, and it will verify that it's actually concurrence, that is actually safe, multi-threaded safe, that you can use it for multiple threads and so on. I read some papers that will help to implement concurrent storage, and I really want to implement something that will scale up to like 64 cores that you can find on the new bulldozers and AMD CPUs and so on. And I think I have good way to write concurrent stores, but it has to be done separately in the separate store. So by default, MapDB will only have a read-write log, and there will be separate implementation of the storage format separate storage formats that will allow greater concurrency. That brings another change. If you remember, MapDB 3 had loads of dependencies. Like there was Google Guava, it was like 3-4 megabytes. Then Kotlin and Eclipse collections and so on. And then the size of the MapDB, if I count all the features which I would like to put in there, the jar file will grow to like 50 megabytes. So I decided to split. This was also causing problems with the release schedule and versioning. Basically, some dependencies require Guava 1 or 11 or 20 and so on. And so this single monolithic jar file with loads of dependencies had loads of problems. I decided to split MapDB into several jar packages, into several modules. There will be a module with MapDB core, MapDB cache, MapDB arrow MapDB, and so MapDB is Guava with all the collections from Guava and so on, and hopefully that will simplify a lot. Dependency management. The only dependency that I decided to keep is Kotlin runtime. Most of the MapDB is written on Kotlin. I think it's a great language. I think if I want to write parallel code that is traversing graphs and trees and so on, Kotlin is great for this. It also allows different backends, so it basically has loads of interesting technical features, and I decided to use it over pure Java. Hopefully I will be able to simplify dependencies a lot and basically provide some sort of experience that is very similar to the old version or MapDB 1, where there was single jar file with 100 kilobytes and no dependencies. I think it will be possible to keep this sort of experience and very simple use for developers. Okay, now this is kind of not important right now, but it's more like vision of where MapDB 4 should go. If you remember data pump in all the MapDBs, it allowed to create B3 maps or tree maps in the streaming fashion. So we had sort of source of data, and you could create a data structure using append-only operation, using own streaming append-only operation that could basically maximize the speed of the hard drive. I don't know, like 100 megabytes per second or maybe 1 gigabyte per second. Because it's a streaming, because it's an append-only, it's not using random seeks. It's very, very fast. It was using, internally it was using some sort of extra merge sort and some interesting algorithms. But I think it has way more potential, and if I would expand it, this data pump thing to all collections, not just B3 map, but hash map and queues and array lists and so on, it will basically allow it will be like new paradigm on the MapDB 4. It will allow you to create collections very, very fast, or load them very fast, make some modifications, save them again, and it could possibly replace snapshot, it could replace compaction rather than compacting the old store and locking it. You could just pump the data in the new store where it is already compacted. So that's something I really want to focus on. And something related to this, basically, if you know Java 8 streams, it's a sort of language that is like similar to map and reduce or filtering, and so it allows filtering, sorting, and so on. I want to integrate Java 8 streams and with this sort of data pump functionality, that you will take a stream of values, make some modification, filter it, sort it, merge it, and then you will be able to save it on disk, in the collection, or in another data structure. And again, it should be very fast. It should use append-only operation, and basically it should be comparable operations in memory, except if you have a SSD that is like 2 times, 3 times slower than memory, the difference is not that big. But major advantage is that the data will be persistent. So you could, instead of, if you have some sort of data simulation, instead of loading the data every time you are starting the JVM and the computation, you could just pre-process the data, or just sort of chew them, pre-filter them, or whatever, save them in the memory map file, and then you could just freely restart JVM as you wish, and all the data will be waiting there. Basically, I want to continue the paradigm that MapDB is sort of alternative memory model for the JVM. So instead of storing all data on heap, you can decide how much data you want to store on heap. Maybe you have a map with keys that are stored in some sort of fast storage on heap or in memory, whatever, and then values and some sort of expiration data and so on in the temporary store that may be available next time you use it, or it can have different guarantees. It can be slower, faster, whatever. basically sort of sharding and partitioning data. And obviously I want to be integrated with integrate with all the tools that are in modern Java, so Apache Arrow, various gRPC streams, and netty, and so on. So basically, another goal is that if you are doing some sort of processing, you should be able to load the data from the Apache Arrow tables or some sort of database, do the chewing, say them in the MapDB storage or Apache Arrow format, and so on. And you should be also able to send data over network using byte buffers by bypassing CPU cache and so on. So integration with netty and so on, other services. Okay, so current status. I worked on the MapDB in kind of quiet for the past 3 months. I haven't really updated the Git because the amount of code. I haven't really updated the GitHub much because I basically keep like 20% of my code. I always rewrote, throw away, and it was kind of embarrassing. I have some sort of working version that is kind of good starting point. I will upload it to the GitHub in a few days. It's passing some unit test. And I want to go towards memory map files, towards temporary storage, basically some sort of Java maps with expiration, and in a few weeks I should have a working MapDB core that is like minimal version of MapDB, sort of similar with amount of features to MapDB 1, maybe JDBM 3, which is even older version. And once I have that, I will start implementing more fancy features like concurrency and so on, and hopefully bring MapDB to the mature databases, or between proper databases and database engine and so on, because it's taking a long times, and there is basically, it's kind of confusing what version what to use and so on, and I just want to have something that's actually working. Okay, thanks. Thank you if you are still actually interested in MapDB. Hopefully, thank you for your patience. Hopefully, you haven't lost any data with MapDB and so on. And let's see how it goes in the next few years, next few months, next few weeks, and so on. Okay, good day. That's all.